update the local copies because I know this one was updated relatively recently.
Okay.
Just let's see. So Siddharth is here. He said. I think apart from being actually now in the room, everyone is here.
Oh, there you are.
Oh. How do you sneak up on us like that?
And you have a mic. Let's give you a mic. Here you go. Let's give you. No, this is the complicated one. Let's give Siddharth the one.
Yeah,
with,
that's
with one button.
yeah, that's probably a good idea.
Okay.
Yeah.
That makes things simple.
Give me a sec. 29. Does that look anything like what you want to talk about?
Yes. Okay. Too many buttons. There we go. Okay, welcome back, everybody. About to get started. And our first speaker after the break, but the last speaker in this session, is Siddharth Kashyap from Intel. And he's going to talk about deep learning under the hood.
Yeah.
Welcome.
Let us see this works. Okay. Able to hear me? Yep. Okay. So looks like the coffee worked, and you guys will stay energetic. Okay. So thank you for having me here. And today we'll be speaking a bit about our experiences with deep learning, and we'll be looking at quite a few popular deep learning benchmarks, and we'll understand what the key hotspots that we found were, and then we developed a small tool called Blast Interceptor. We'll go through the motivation for the need for that, and using that tool, we did an analysis of the benchmarks itself, and we'll be going through that. Okay, so this is the agenda, and I don't think anybody in this room has not heard of this, so I don't need a motivation to explain what deep learning is. But the key point is that deep learning is poised to be one of the major workloads that will be deployed on the majority of the compute infrastructure. We all know that, and Richard rightly explained that. They are now trying to scale out deep learning models for science, which has scale-out capabilities of up to thousands of nodes. So this is going to be one of the key components that will be running in, and HPC and deep learning are tightly connected to each other. So if you see articles from Baidu and others, so HPC is the key component that makes deep learning as efficient as it is. So they can deploy it on any infrastructure, but the key fact is that you'll have to know your traditional routes in HPC for you to understand how you can deploy this, how you can scale it out, how you can actually solve problems that are of interest to the community. So that is very important. And if you look at what exactly happens in deep learning, it basically translates to, this is from 1,000 feet. It translates to, say, calculus and linear algebra, which basically translates back to manipulation of large matrices. We'll see that in detail in the next half an hour or so. And the deep learning frameworks rightly rely on BLAST libraries for it to perform these operations. And we'll also see the fact that the single precision matrix-matrix multiplication routines are actually the dominant ones. So these are the benchmarks that I was speaking about. So basically, if you see here, these are divided into convolutional neural networks and recurrent neural networks that are of interest to us. So here you can see the fact that majority of the deep learning workloads that we see for image recognition and others belong to the category of convolutional neural networks, which further belongs to the category of feed-forward neural networks. So that happens to be one of the, say, major kind of deep learning workloads that are deployed. But deep learning is not just useful only for image recognition and computer vision and other tasks that media focuses on, but there are a lot of other things that deep learning is currently being used. And one of the major areas that deep learning is being deployed and actually replacing traditional methods is in natural language processing. And we use one of the benchmarks called AMU-NMT, which is from the University of Edinburgh and developed in collaboration with the Alan Turing Institute. So we'll be looking at that as a benchmark. So basically, we have chosen the winners of the competition called ILS-VRC, which is large-scale image recognition challenge by Stanford, and then the winners of that being the AlexNet, GoogleNet, and VGGNet, and these are all convolutional neural networks. And for those who have not seen these workloads before, so you can see that it translates to us stacking up layers of activation and pooling on top of each other like what you see here. And then when you combine this entire nonlinearity into one, you get a neural network model. And when you deploy this is when the machine learning happens. And you need to train these models for you to actually get the results out of it. So I cannot get into the full detail of these or how the convolutional neural networks are implemented in such short time frame. But the motivation being, OK, if you look underneath those benchmarks and run a hotspot analysis using VTune, you will find that irrespective of the neural network architecture, for convolutional neural networks, that is GoogleNet, AlexNet, or VGGNet, the SGEMM routines are the key bottlenecks. So you can see, for example, on VGGNet that the Mike SGEMM kernel 0 occupies nearly 31% of the total runtime. And the routines like im to call, call to im are basically feeders for you to actually translate and transform data so that you can use SGEMM for convolution. So if you look at the top 5 or 10, and I've actually highlighted everything in green, you can see that SGEMM routines are the key, irrespective of the kind of neural network that you're using for convolutional neural networks. Okay, so this is the key motivation. And we use Caffe, and we did 100 iterations on this, and this was done on a KNL single node. Okay, so this is not the case with just Caffe or the neural network implementation. We also tried to compare and find the hotspots across benchmarks as well. And we found that the story is actually repeating. It's the same thing. We can find that SGEMM is the hotspot even for Theano. Okay? So irrespective of the kind of benchmark that you're using or the framework you're using, the SGEMM routines dominate the performance. So if you get your SGEMM implementation right, you can actually have very good performance out of deep learning frameworks. So now that we understand that SGEMM is supposed to be the key bottleneck, we thought that we need to understand those routines better. So we wanted a tool that can give us the insights into each of the SGEMM routines. What are the key matrix ranks? How much performance are we able to get for each matrix rank? And what is the IPC? And can we do something about the counters itself? Can we understand how the hardware is behaving with respect to those ranks? So to do that easily and non-invasively, we designed a small tool called Blast Interceptor. So Blast Interceptor is basically an LD preload based small library that basically profiles gem calls. Okay? And this basically simplifies the analysis of any binary or even partially interpreted frameworks like TensorFlow. So if you have a binary that has gem calls in it, you do the LD preload like many other profiling tools. And if you do that, you basically have the capability to plug in your own custom routines. For example, if you have a novel idea that implements SGEMM better, then you can basically swap that without actually changing the binary and see what happens. So that is the custom routine, and you can choose your hardware counters in a small config file, and you can easily extend this to other BLAST functions. We've done this for GEM, and that automatically generates reports for you to visualize. So it currently gives us the matrix ranks, the calls made, the frequencies, the fraction of the theoretical performance. This is the roofline analysis, and the ranks versus the instructions per cycle that it achieves. And yeah, we can configure minimum metrics based on what you're interested in. So this is the flow. You just configure the metrics of your choice. You tell what you want to get out of your profiling itself. You set your LD preload environment variable, and then run the library. So if you do that, you have the option to choose your custom implementation if you are trying to optimize and bring up your own GEM version, or you can choose the traditional BLAST implementation like MKL or OpenBLAST. Okay? So this was the tool we developed, And the results that you see are obtained from the tool that we developed here. So before we speak about the results itself, the experiment setup, so we did everything on a single node KNL. And the clustering mode was set to all, and MCDRAM was in flat. And we measured the stream maximum memory bandwidth to be 380 Gbps, and we used Intel Compiler 17, and we used PAPI for us to get the hardware counters, and we used Caffe and Theano, as you'll see later. Clear? Okay. So the first thing that we need to understand for us to get the feel of what kind of matrix multiplication is happening in deep learning, we need to understand what is the frequency and the matrix ranks that are used here. So here you can see that the key distinguishing part of, say, the deep learning workloads when compared to HPC ones is the fact that deep learning has a lot of tall and skinny matrices. So I've just put in one example wherein the M and K for the SGEMM call happens to be 4608, 196, and 512. So these are not your dense and square matrices that are very well optimized. So if you deploy a TensorFlow or a Caffe-based convolution neural network model, it basically translates to matrix ranks like these. And you can see that when I say flops here, it is the total number of floating point operations that are contributed by that particular matrix rank. So you can see that the highest contributor is a matrix rank of 256, 3136, and 2304. So these are the large matrices that are found in the workloads. So we'll do the similar analysis for Google and Net. I don't think you can see this. Okay, so, but for the sake of brevity, we can see that these are the kind of matrices and the ranks that are actually involved in your convolution neural network run. So given that we cannot actually represent this in any more detail, I have actually taken the top 100 ranks from this particular run. And here you can see that the story is actually the same, wherein you find that the tall skinny matrices like 192, 576, 3136 are contributing to the number of floating point operations that were performed by this. Okay? So this is the case of a recurrent neural network benchmark. And here the story is actually even bigger, wherein you see the matrix rank sizes to be something like 12, 85,000, and 200. So this is the analysis of AMU and MT, the code developed in collaboration with the Alan Turing Institute. So we have these kind of matrix ranks that are not found in traditional applications. And if we are doing something, we have to optimize these. So to understand that further, we need to understand what is the performance that is being achieved for those matrix ranks. And the BLAST interceptor gives you this information out, wherein you see that, say, a fairly dense and big matrices are actually performing really well, but it suffers for tall and skinny matrices. Okay? So that is, again, the story for GoogleNet, which is the 2014 winner. And here you see that for the ranks at the bottom end of the curve, then you have lower performance, but you get good performance when you compare, say, as your matrix size grows. Okay? So this was the analysis that led us to understand what's exactly the instructions per cycle that the code is achieving. And then when we found that the highest performing matrices were achieving an IPC of nearly 1.8. And the skinnier matrices have lower IPC, as we can expect. So, okay. Now, to understand that even further, we need to understand what is exactly the capability of the machine and where the code is at this point. So the BLAST interceptor gives you the roofline ratio as well. That is, for that particular matrix rank, what is the achievable G-flops that I can get, and what exactly is the code giving you. So that is the ratio that is seen here. So the roofline ratio for VGGNet happens to be something like this, wherein you see that for matrix ranks like 512, 784, 1, it is actually achieving very low G-flops, but it is actually near the highest performance that can be theoretically achieved. But there are these matrix ranks at the far end like 4096, 25088, and 64, which can be optimized further. Okay? So The same is the case with GoogleNet as well, wherein we find that we are able to achieve nearly 3.5 teraflops on a single KNL for some matrix ranks, but we are at the far end of it for certain other matrix ranks as well. So here you can see the progression of the frequency of the matrix ranks versus the gigaflops that it achieved. And you can see very clearly that the blue line represents the roofline ratio, and the red is the G-flops that it achieved. And we cannot do any better on these matrix ranks. So for us to understand this further, I told you earlier that we have the capability to plug in hardware counters. So that was the story, as in you have your matrix ranks, you have your matrix ranks that are supposed to be resident in L2, but they're not actually doing anything, and you need to understand why. So Blast Interceptor basically provides you the methodology for you to plug in any hardware counter of your choice, and you can understand what's exactly happening in your hardware. So this is a demonstration of what we tried doing, and here you can see that the total instructions, total cycles, all loads, L1 misses and L2 misses were configured to be the metrics of our choice. And when we did that, we find that there is a very high load rate. That is, 2/3 of the instructions are actually loads. And the L2 misses are very low. The L2 miss rate is low. You can compare, this is basically the ratio of your L2 miss loads divided by all loads, and that comes out to nearly 0.6. And so the performance of the SGEMM call is not due to high miss rate, right? So the performance of the SGEMM calls of interest are due to something else. It is due to the implementation of the kernel itself, and it is not due to the fact that you are getting many L2 misses. Okay? So the data is actually resident there, and you have the scope for you to do something better. And we also saw the fact that I was speaking about the custom SGEMM implementation. So what is the motivation for us to do this? So the fact is that sometimes you want to understand what exactly is the effect of precision, as an example. So precision studies is one thing that is of very high interest to the community. They want to, so you can see a lot of news about, say, deep learning being done in 1 bit. That was a paper that was written by Microsoft. And then you see that 8 bits are also sufficient. And sometimes you see that there are now hardware is coming up with just half precision implementation. So what exactly is the effect of precision? So if you are trying to do this kind of analysis, you can write your own SGEMM call and basically implement the SGEMM in half precision or anything of your choice, and then try to see what happens. So we tried mixed precision on this. That is, we used F16C intrinsics, and we converted all the floating points matrices that were actually coming in, and then we did the accumulation in single precision. So when we did this, we found that the performance of the custom SGEMM implementation with respect to MKL was actually 1:1. So if you have a mixed precision implementation with a rounded accuracy with respect to half precision, then you actually get the same result on MKL. Okay? So this is a demonstration of the kind of things that you can do with the custom implementation feature. So you can choose to do any implementation that you think will optimize the performance and just plug in. And this was just an example. So I finished a bit early. Okay. So the summary of that being, SGEMM happens to be one of the, say, key routines in deep learning. And tall and skinny matrices basically pose a challenge. And we can use the Blast Interceptor, the tool that we have developed, to actually understand what's happening. And Intel has actually been working hard, and you can see that they have actually released MKLDNN, libXSMM to address these issues exactly. And the latest versions of Intel frameworks that you see are actually trying to alleviate all these problems and make sure that they use all the optimizations possible for them to get the maximum performance out. But this is not the case with, say, custom frameworks like AMU and MT that are being developed. So we have to, if you are developing a deep learning framework, then you are better off actually using the primitives that are developed by Intel and using those. And we are trying to do many things with respect to precision as well. And the ongoing work, we are trying to understand what exactly is the inflection point where we can say that we can do a drop-in replacement of a neural network that was written in single precision and implement that in half precision. So basically, neural networks have the problem of the big hyperparameter space. So you need to tune whatever is your learning rate, your weight initialization, and you have like hundreds of variables that you need to control for you to actually converge. So if you do a drop-in replacement of single precision with a half precision implementation, you will not converge. So you will have to make sure that you tune the hyperparameters. You will have to make sure that your learning rate is tuned, your weight initialization is tuned, your biases are tuned, so that you get your convergence right. So what we have seen is that even the slightest change in accuracy results to, say, the neural network not converging, and you get lines out of it. So we want to find out exactly what is the inflection point of implementation versus the precision and understand what's happening. So that was the motivation for us to develop the custom SGEMM call that we saw there. And we are trying to look at various kinds of convolution neural network performances. So recurrent neural networks is one of the things. And we are also trying to see what exactly we can do with respect to multi-node performance. So before I conclude, okay, so as a thank you, I just want to say that, this was a joint work that was developed by myself, Angus, who is sitting in the corner, and Professor Peter Boyle. So we work very closely with Professor Peter Boyle from the University of Edinburgh, and he leads the team in ATI, the Alan Turing Institute, and leads the co-design efforts. And this work was a part of that, and we work for the Innovation Pathfinding and Architecture group within DCG, and yeah, we all work from Edinburgh. So thank you.
Thank you very much. I think, again, we have a couple minutes if anybody has any quick questions.
Yeah, nice talk. I have a question. Is the blast interceptor available, freely available, open source, or?
No, it's available within Intel as of now. We'll make it available.
Okay.
Yeah.
Okay, thank you.
Anything else? Okay, well, thank you.
Thank you.
Willis, he's been a great member of IXPUG, along with Matthew for the last couple of years. So I'm looking forward to hearing your talk. So welcome, James.
Thanks. Does it just continue on from?
Oh, yeah. Most important bit.
No, you have to give that talk.
Sorry. That's the one.
Presentation mode or?
No.
Just go to view.
Which one? Great. All right. Thank you very much.
Thanks. So my name is James Willis. I'm from Durham University and I work at the Institute for Computational Cosmology. And today I'm going to talk to you about the SIMD optimizations I've been performing on the cosmological code called Swift. I'll just start by saying that Swift's been created as a collaboration between the ICC and the School of Computing Sciences at Durham and various universities, and I'd just like to say it's fully funded by the IPCC at Durham University. So I'm going to start by outlining the problem that I want to solve, and then I'm going to go on to the solutions that we've come up with to solve it. And then in the second part of the talk, I'm going to go on to the SIMD optimizations I've been performing on the code to speed it up. Okay, so Swift utilizes smooth particle hydrodynamics to solve the problems, the cosmology problems. So basically, we've got a group of particles, and for each particle, we need to interact it with its surrounding neighbors within a smoother length h. And once we've calculated this, we use it to update the particles' positions. So we vary h depending on the density of the region to keep the number of particles fixed. So in a sparse region, you'll have less neighbors, so we need to increase the smooth length to keep the number of particles fixed. And once we've found the group of neighbors, the actual interaction itself is relatively cheap to compute. So we split our problem up into a series of cells. So basically, we want to interact all the particles in cell A with all the particles in cell B that are within a smoother length h. And as you can see from this, that the majority of particles won't actually interact, as most of them are not within distance of each other. So a naive solution to this is to do a brute force double for loop over all the particles in cell A and all the particles in cell B, and calculate the separations between the particles, and just to check this condition is true, whether they're within the smoother length or not. But as you can see, there is a lot of unnecessary distance calculations involved in this, which can lower the performance of the code. So the solution that we've come up with is to form what's called the pseudo-Verlier list. So what we do is we project the particles onto an axis which joins the center of the two cells, and we sort the particles depending on their position on this axis. What this allows us to do is to reduce the number of candidates that we actually calculate the 3D distance to determine whether the particles interact. So as you can see from this is that we project the particles onto this axis here, and then we sort them on the axis depending on their position, and we take one particle and we look at its smoother length, and then we can see from here that none of the particles here will ever interact because of the distance from the smoother length. So we only need to calculate the 3D distance from this group of particles here to check that the condition that r squared is less than h squared. The diagram here just shows how it maps onto the SIMD strategy. So we have the one particle here, and we take a list of 8 candidates from the second cell here. We perform the interaction, check whether they interact, mask them, and then update particle pi here. So this is just some pseudocode which utilizes the algorithm. So basically, we sort the particles first, and we've got the double for loop again, as in the brute force. But now we've got this extra condition which checks that the distance of the particle in cell B is less than the smooth length of the particle in cell A, which reduces the number of unnecessary distance calculations. So in the second half of the talk, I'm going to go on to the SIMD optimizations. So first of all, in Swift, we have this global particle array, which is an array of structs. And as you know, when you're loading the positions and the smooth lengths into vectors, you'll have non-contiguous loads. So there'll be strided access, which will reduce the performance. So what we do is we take all the positions in the smooth lengths and copy them into a structure of arrays so that they're all contiguous in memory. So when the vectors are loaded, there's uniform memory access, which improves the performance. Something else I'd like to point out is the positions are stored as double precision in the global array of structs. So what I do is I convert them to the local reference frame between the two cells so that I can perform the operation in single precision, which increases the performance even further. Okay, so each cell, just because of the geometry of the problem, has 26 surrounding neighbors. So we have different types of cell pair interactions. So we have the face-on, where there's 2 cells next to each other. Then we have edge-on, and then corner-on. And these all have varying numbers of interactions just based on the geometry. So what we want to do is we want to lower the overhead of populating the cache. So we might not want to form the cache and perform vectorization on, say, the corner interactions, for example, because there's only a low number of interactions. So in this optimization, we want to lower the overhead of populating the cache. And to do this, what we do is we have the 2 cells. We start from here. So we have particle pi, and we check the smoother length and see if it's within range of any of the particles in cell B. And in this case, it's not. So we move on to the next particle. We check again. Nothing's there. and move on to the next one, and so on and so forth, until we get to a particle what actually interacts with the first particle in cell B. So what we can do is what we can tell from this is that these particles here interact with no particles in cell B. So we can just read a subset of the particles into the cache, which reduces the number of reads into the cache, which improves the performance. The next optimization we want to perform is we want to reduce the number of particles we loop over in the neighboring cell. So, for example, we use another array called a maximum distance array to find this. So again, we've got the same setup. Have a particle here. We work out its distance with the smoother length on the axis and populate maximum d here. The next element, though, we take this particle, calculate the distance again, but we take the maximum of that distance compared to the one before. And then we do that for the next element, and so on and so forth for the whole array. Now, how we use this is we take the last particle in cell A here, and we take the maximum distance, and we compare it to the distance of the last particle in cell B. So as we can see from here, it's outside of the maximum distance here, so it doesn't interact. Move on to the next one. It's still not within the smoother length here, within the maximum distance. So move on to the next one until we meet this condition, so we know that this interacts. Well, we don't know it interacts, but we can then calculate the 3D distance to check that criterion. But what we know is that none of the particles in here interact with any of these two particles here. So what we can do is when we move on to the next particle here, we can start from this location here without having to check these two particles. So this allows us to reduce the number of calculations even further to improve the performance. So now I'm going to move on to actually calculating the interactions themselves. So to calculate the density on a given particle, we take the sum of the masses of its surrounding neighbors with this weighting function, which is just a low order polynomial. Now, what I've chosen to do here is to calculate the vector mask, which is just the criterion that the distance is less than the smoother length. Then actually calculate the density itself. What I've chosen to do is to take an intermediate vector sum of the density. So you apply the mask to this density vector here and store it in this vector here. And then what I continue to do is loop over the rest of the particles in cell B and continue to update this vector. And what we have at the end, when we've gone through all the particles in cell B, is we have a total sum of the density on one particle pi. Then I perform a horizontal add on this and update the density of pi. This reduces the memory overheads of continually having to update pi from all the interactions. We can just store them in here and then just update them once at the end. This is just some pseudocode again. So we set the density sum to 0. We loop over all the particles in cell B, and we update just the density sum. Then we perform the horizontal add here and update particle pi. This was just to show the difference between the AVX instructions in AVX 512. So in AVX 512, you have this 16-bit interaction mask, what you use from comparing the smoother length to the distances. And in AVX, I think you have to do an extra step to get the mask. One final optimization was with the cache, we padded the elements so that when it come to doing the loops, there was no serial remainders, and we can just do the loop over a multiple of the vector length and just pad the cache and then mask the result to improve the performance. So the performance results were gained for AVX, AVX2, and AVX 512. So that's on Sandy Bridge, Haswell, and the KNL we've got with 64 cores. So the results I'm showing here. The first column shows the raw particle interaction. So this is when you've got the particle and you have a whole list of neighbors contiguous in memory. So as you can see, for AVX, we get 6.5, and roughly the same for AVX2, and 17x for AVX512. These are similar results that I think Luigi from LRZ presented in Toulouse in September last year, what he did with Gadget. The next column shows the speed up of the algorithm vectorized over the serial version of the code unsorted. So that was the brute force algorithm I outlined earlier. So as you can see, just by moving over to the pseudo-Verlet list, we can get quite a lot of performance increases there, although this does include the vectorization performance increase. And finally here, we compare the serial pseudo-Verlet list with the optimized pseudo-Verlet list with SIMD operations. So we get 2, 2.3, and then 3.9 on AVX512. So this includes like the overhead of populating the cache also. And then that was just to conclude that we've used the pseudo-Verlet list to improve the inherent algorithm, and we've used various optimizations with SIMD to improve the vectorization. And in future, I want to reduce the overheads even further and improve the vectorization efficiency. And that was it. So thank you.
Thanks, James. So any questions for James?
Oh, is it?
Oh, we're going to do that right at the end, sorry. Yeah. So next up, we have Vladimir Mironov. I hope I'm pronouncing your name nearly correctly.
That's 27. Oh, it's on. Test. 1, 2, 3. Yeah, John. Okay, we won't do that. Okay. Okay, my name is Vladimir Mironov. I'm from the Lomonosov Moscow State University. I'm also a PI of Intel Parallel Compute Center in Lomonosov Moscow State University. This Parallel Compute Center is devoted to the optimization of quantum chemistry code called General Atomic and Molecular Structure System, or briefly abbreviated as GAINS. And today I want to tell you about some of observations from my work that I found to be interesting to the community. I will talk about optimization of transcendental, or also known as special functions that are used in quantum chemistry. They are quite often in quantum chemistry. For example, if you calculate the electrostatic repulsion between the electrons, you need them. Electrons are not particles, actually, in quantum mechanics. They're not point particles, they are quantum particles, and they're represented as with a wave function. As wave function is also represented through the more simple basis set functions, and one of the most common choice for these basis functions are Gaussians. Thus, you frequently need to calculate the integral like that, representing the electrostatic repulsion between Gaussian clouds. It is the simplest case, and even in this case, you need the exponential integral that is quite common not only in chemistry, but also in some fields like statistics, economics, and etc. In more complex case, you need to calculate more complex integrals, and the basis set functions are product of Gaussian and three-variate monomial. There are multiple algorithms for these integrals calculations, and all of them require calculation of special functions specific for that algorithm. The examples of these functions are Boy's function and roots and weights of special orthogonal polynomials called Riesz polynomials. In this work,
today I'll talk about the RIS polynomials, roots, and weight calculation. The calculation of this function takes significant amount of computational time when you need low-order RIS polynomials. In this case, it can take significant amount of computational time. The algorithm that is used in most quantum chemistry codes is based on the old work by the developers of this method. It involves a lot of multiple heavy operations like square roots, reciprocals, exponentials, etc. If you use a lot of them, your program becomes backend bounded, and it performs very slow. Thus, we implement a more simpler fitting for more simpler approximation for these functions to optimize the performance of the code. In this work, we are focused on single-thread performance because the code, even for the original implementation, is quite small and can fit even an L2 cache. So the scaling is very good, and it also doesn't depend on the memory and clustering mode on Intel Xeon Phi. In this work, we also compare the performance of various approximations for Intel Xeon Phi and Xeon CPUs. We have used Xeon Phi 7250 node and the Intel Broadwell node E5-2697. In this work, we used polynomial approximation. It is a very common way to approximate transcendental functions, and one of the most important example maybe it's a spline fitting. The qubit splines are actually third-order piecewise polynomial approximations. The advantage of polynomial approximation is that they require only very simple operations that can be easily vectorized and doesn't introduce a lot of pressure to the pipeline. Only multiplication, addition, and FMA operations are needed. In most cases, it is the polynomial approximation is unstable because if you need to get a high precision, you need a long polynomial expansion, and thus it can be numerically unstable. So the way to solve this problem is to separate the interval of arguments into multiple intervals and use shorter polynomial expansion. This is referred as piecewise polynomial approximation. And you need to balance, to find the balance between the degree of polynomials and the number of interpolation intervals, because if you use few but large interpolation intervals, so you have long polynomials that will use a lot of clock cycles. If you use multiple small intervals, you use shorter polynomials, but the code becomes more complicated. And it introduces optimization issues with the compiler. So here is an example of how we make, this is a synthetic test that we use to determine the optimal amount of interpolation intervals. You may think that if you put this code sample into the loop, it will not vectorize, yet it did, if the calling function was simple enough. On the right side of the slide, you see the benchmark results for Broadwell and KNL node. On the Broadwell, we see approximately 2 times performance improvement when you switch from 7 interpolation intervals to 2 interpolation intervals. So it's only if and else case in here. The most notable performance improvement was observed when switching from 6 to 5 interpolation intervals, and it's about the overall performance improvement is about 2x. For KNL, the improvement was about 10x from 7 to 2 interpolation intervals. And the most notable improvement was between 4 and 5 intervals. So the reason why it doesn't optimize it, the reason why it doesn't optimize at 5 interpolation intervals like on Broadwell node is that compiler heuristics decided that the loop body is heavy enough, it cannot, and the vectorization impact wouldn't be too much. However, it is not true if we alter the behavior, compiler behavior using dash vec threshold 0 flag. We successfully vectorize the code at the number of intervals of when the number intervals is equal to 5. Here is an example of when we compile our application for KNL without SMD intrinsics and without vectorization. You can see that performance improvement is very modest, and here it is equal to the performance of KNL with vectorization. That's the reason was that here is a compiler decided to vectorize it. Here is a brief introduction in how we calculate actually polynomials. There are different calculation schemes. The example are Horner scheme, when you calculate the polynomials step by step using FMA instruction in chain. Another scheme is a S-string scheme, when you separate the polynomial calculation in a way like a binary tree. So there are a lot of internal parallelisms. On each step, you calculate multiple FMA. You use multiple FMA instructions, so the code can be vectorizable even if you calculate only 2 or 3 of such polynomials. And there are also custom schemes, but they are very hard to find an optimal schemes because the amount of them becomes very large when the polynomial degree grows. So here are the benchmarks for the optimized code. Here we also introduce 2 additional techniques called, we use Chebyshev polynomials for fitting. They improve the precision of the fitting. And also we used rational polynomial approximation when we approximate not by a single long polynomial, but rather with a fraction of 2 smaller degree polynomials. Thus, it is like interchange of 1 division with multiple multiplications. It has theoretically higher precision for fitting, but we didn't observe it for all cases here. There are the results. The original implementation contains 8 if cases for number of roots 1, and it is eventually doesn't vectorize on KNL. So there are polynomial expansions and Pade approximations, vectorizes for Broadwell, and quite good. So we get here approximately 2.5 performance improvement. On KNL, the example with 12-order polynomials does not vectorize. However, 32-order polynomials with only 2 interpolation intervals and Pade approximations vectorizes quite well. The overall performance improvement is approximately 10x our original implementation. For the number of roots equals to 2, the situation is the same. So here the performance improvement is not so large, but however, it is approximately 8x performance improvement versus original implementation. Here are some notes that for the algorithm. First, that asymptotic condition when the x is very large, at the last case, holds approximately in 50% of all cases, and we adapted our benchmark to match this condition. We have used range reduction algorithms that use mapping from the power of 2, for the intervals from 0 to power of 2 to 0, 1 intervals. It was done for numerical stability of polynomial evaluation and to improve the precision. And also using powers of 2 allows us to using numerical shifts and additions instead of very costly divisions. Also, we use S-string schemes for polynomial evaluation, and the compiler flags are presented also on this slide. The using of interprocedural optimization and inlining are crucial to get the optimal performance. So our further work is devoted to optimization of the Boyce function, moving the code base to the C using intrinsics, and publishing it to the separate library. Also, we are working on our range reduction algorithm, probably to get better precision of our approximation. I would like to acknowledge the tools that I use in my work. First, there are Intel tools that helps me to find out problems in the source code. Fitting coefficients were found using Python and NumPy and SciPy libraries. And also, I used these tools to fitting and finding polynomial scheme evaluations. I want to say the result that Xeon CPUs and second generation of Xeon Phi architectures are still very different architectures, and piecewise approximations should be used with care on Intel Xeon Phi second generation. And to compete with Xeon CPU, Xeon Phi programs on Xeon Phi must extensively use vectorization. So, thank you for your attention.
Thanks very much, Vladimir. So next up is Marcus Kunish.
Well, good afternoon, and thank you very much for giving me the opportunity to speak here. I'm going to talk about our efforts to do numerical general relativity on Intel's Knights Landing. I'm a PhD student here at the maths faculty in Cambridge, and my co-workers are Alejandro Duran from Intel, Juha Jõke, one of the organizers of this conference, and then Saran Tanyazunagun, a former PhD student here who now works for DeepMind. The code we're going to use for this optimization is called Chia Chombo, and it's developed by these 8 physicists here, again with the help of Alejandro and Juha. The GR obviously stands for general relativity, and the second part of the name stands for the adaptive mesh libraries we use. We use the Chombo adaptive mesh refinement libraries developed at Lawrence Berkeley National Lab in the US. This is an outline of what I'm going to talk about. I'm going to start by giving you a brief overview of numerical relativity, and then I'm going to tell you what our code looked like before we moved it to KNL. The main section of the talk is, of course, going to be about our optimizations to the code for KNL, and then I'm just going to quickly summarize and give you an outlook of what our future work is. Okay, I think it won't come as a surprise to anyone in this room if I tell you that Einstein's equations are really hard to solve. And in particular, we can only find analytic solutions in very few cases. So generically or generally, we will have to use computers to solve Einstein's equations. And that's what numerical relativity is all about. Numerical relativity has a lot of applications, but the most important one comes from gravitational waves. I'm sure you've all heard about the excitement last year when LIGO announced the first ever detection of gravitational waves. These gravitational waves come from a black hole merger more than 1 billion years ago. And numerical relativity is one of the tools that we use to predict what the observational signature of such a gravitational wave event is going to look like on Earth. So how do we do this? Well, we rewrite Einstein's equations as an evolution system, and we use this evolution system to evolve initial data forward in time. We present all of this data on a rectangular grid, and then for each grid cell, we calculate spatial derivatives using finite difference stencils. We then, once we have those derivatives, we can calculate the right-hand side, and then we can just perform a time step using some explicit time integration scheme, such as RK4. The complication with all of this is that the right-hand side is very complicated. So the challenge is going to be to optimize this right-hand side such that it runs well on Intel's Knights Landing. There's an obvious layer of parallelism in all of this. You can just split up the computational domain into boxes like so, and then distribute all these boxes among the ranks. Now, of course, because we need to calculate spatial derivatives, we need to surround our boxes with ghost cells so that we can fit the finite difference stencils even at the edges of the boxes. Now, the problem is that because of the high accuracy requirement in numerical relativity, we need to use very wide differentiation stencils, which means that we need to use up to 4 ghost cells. And as you can see, that makes it completely unfeasible to use a small box like this because it's going to be completely dominated, completely overwhelmed by the cost of communicating these ghost cells between the ranks. And in our experiments, we've found that the minimum feasible box size is roughly 32 cubed. This MPI parallelism, this box parallelism, has very good strong scaling up until the point where even with the minimum feasible box size, you just run out of boxes for your ranks. And for a standard problem, this happens at a few hundred cores. So you cannot, or a few hundred ranks. So you cannot scale to more than a few hundred cores if you only use this MPI parallelism. But for the problems we study, we needed further speed up. And because you cannot use the box parallelism anymore, you need to move beyond this parallelism and use new layers of parallelism. And this is where it gets exciting, because that's precisely what the KNL is about. It's all about kind of finding these new layers of parallelism, using the wide vector width, using all these cores that you have for the node. So the challenge we set ourselves was to optimize GeoChombo for the KNL, but do this entirely with new parallelism. So we only want to use one box for the KNL. And we then want to use vectorization and the cores we have to speed up this one box. In the short term, this might make our work much harder, but in the long term, it will give us better strong scaling because we can still use the box parallelism to scale to more KNLs, and therefore we will get a much faster application that way. Okay, so as testbed, we're going to assume that we've exhausted this MPI box scaling. We've ended up with only one box per KNL or per node. And then we're going to optimize the time it takes to do one time step for this box. As hardware, we're going to use this KNL in cache quadrant mode because we want to put only one box on this KNL. And we're going to compare this to a single socket Broadwell. Why a single socket Broadwell? Well, the point here is that, as I said, our MPI parallelism, this box parallelism, is very good. So in reality, we're going to exhaust this to the full extent and make the boxes as small as possible. Say we then end up with 100 boxes. On the KNL in quadrant mode, we can actually use 100 KNLs and just put one box per KNL. But with the dual socket Broadwell, at the moment, the only way we would have to deal with the NUMA on the dual socket Broadwell is to use one box for each Broadwell. So in total, for the same problem, at the moment, we could only use 50 dual socket Broadwells. And therefore, at the moment with our code, it would simply be unfair to compare the KNL to the dual socket Broadwell because we can use twice as many KNLs in the end. Okay, but before we start this testbed, we have to implement some OpenMP parallelism so that we can use all the cores on the KNL. And the way we do this is as follows. I've said we ran out of boxes at this point. We only have one box per rank. And then within this box, we do an OpenMP loop over the Z and the Y coordinate in the box. And then we calculate the right-hand side. As I said, we're going to not include this x-coordinate in the threading because we're going to use this for vectorization later. Okay, so here I've started a table with speedup compared to the initial code with OpenMP on the Broadwell. And as you can see, initially, the kernel is actually 30% slower than the Broadwell, even a single socket Broadwell. Okay. Throughout the process of optimizing, we used vTune to guide our optimization. This is the initial vTune profile. So as you can see, we actually spend 65% of our time just calculating derivatives. So the most important thing is going to be to optimize the calculation of these derivatives. But the thing that immediately caught our attention, of course, was this bad VPU utilization rate. And together with the vectorization report, this told us that the auto-vectorization of the code was very poor. And this isn't too hard to understand because Einstein's equations are very complicated. The evolution system we use looks like this. It's very long, and even this is not fully expanded yet. So if you expanded this fully, it would be twice as long. And as you can see, we have a lot of small inner loops, these summations here. And the compiler correctly decides that it's completely pointless to vectorize those loops. But it's obvious what should be vectorized. It's this outer loop over the x-coordinate, because we don't have any problems with vectorization there. But no matter where we put the pragma in the code, or where we put pragmas in the code, we couldn't get the compiler to auto-vectorize this outer loop over the x-coordinate. So what we decided to do in the end was to vectorize the code explicitly using vector intrinsics. But we have to be careful with this because we don't want the physicist to have to worry about vectorization. We don't want the physicist to see any vector intrinsic, any wrapper classes, or we just want the physicist to be able to write code as they would usually do. And the way we achieve this is as follows. We assume that the physicist has old code for the computation of the right-hand side for each cell. The only change they're going to have to make is to change the data type double to a general data type data t, which they template over. And what GeoTrombo then does is it organizes the loop through the box. It first does the threaded loop over z and y, and then it splits the x loop into SIMD chunks and feeds those SIMD chunks into the right-hand side that the physicist has written in this new class SIMD double. So those are our SIMD chunks. And for the remainder loop, it can just use the standard double and feed this into the right-hand side. But as I said, the physicist doesn't have to worry about any of this because this just happens internally in GeoTrombo. All the physicist has to do is replace double with data t. So in the right-hand side calculation, they might want to write something like this. So here data t out is equal to 1 and then some calculation. And GeoTrombo provides everything that's necessary for this to be possible. So for example, we need to implement the implicit cast from an integer to a SIMD double. We needed to implement the multiplication of an integer with a SIMD double, the addition of two SIMD doubles, and so on and so forth. Internally, GeoTrombo just replaces this with the vector intrinsics for the architecture you are currently working on. Okay, so let's look at the speedup we got through this. And as you can see, the VPU utilization rate then actually goes to 100%. But because we then hit other bottlenecks, the CPI rate also doubles, and we're left with a factor 4 speedup on the kernel. Note that at this point, the kernel is already faster than a single socket Broadwell and would be roughly the same speed as a dual socket Broadwell. Okay, these are some further optimizations we performed. I won't have time to talk about all of them. However, I will point out a few interesting ones. So the first task, of course, was to bring the CPI rate back down again. And after a bit of digging in vTune, we found that the reason for this bad cycles per instructions rate was that we have several derivatives in our right-hand side. And on the Broadwell, several divisions on our right-hand side. And on the Broadwell, this didn't matter at all. As you can see, the time here doesn't change at all. But on the kernel, divisions, or the relative speed of divisions, is slower than on the Broadwell. So eliminating divisions from our right-hand side actually brought the CPI rate back down again and gave us a 20% performance improvement on the kernel. The next improvement I want to point out concerns symmetrization. In general relativity, you deal with a lot of symmetric matrices. And in GeoTrombo, all the user has to do is to tell GeoTrombo that this is a symmetric matrix. And then GeoTrombo is going to store only the upper diagonal part of the matrix on the grid in order to save memory. And then locally, it's going to copy the upper diagonal part down to the lower diagonal part too, so that the user doesn't have to worry about symmetrization. Now the problem is that the way we wrote this, all of this was done at runtime. So at runtime, the core had to decide to copy H11 to just one destination and H23 to 2 destinations. And on the kernel, this led to a lot of branch mispredictions, which slowed down our code. But of course, all this information is already available at compile time. So by making this information available to the compiler, we managed to get the branch mispredictions down, and therefore get another 10% speed up on the kernel. The final optimization I want to point out concerns the way we aligned or allocated memory. In the old code, we just had a standard malloc call, but in the new code, we've now replaced this with an aligned memory allocation, and we align this memory with the huge page boundaries. And what this allows the kernel to do is it allows the kernel to use the transparent huge page mode, and this brought our page walks down, and therefore got us a speed up of roughly 10% on the kernel. Okay, before I finish, let me just show you a scaling plot with the final code we have now. As you can see, so this is only intranode scaling. As you can see, the code now makes fairly good use of all the cores up to 68, but we cannot currently oversubscribe cores. At the moment, it's not, it's actually even counterproductive to use 2 or 4 threads per core. Okay. The starting point of all of this was the end-of-box parallelism. I've told you that because of the wide differentiation stencils and the many ghosters that we have, there is a minimum box size that we can use. And this minimum box size means that for a standard problem, we cannot chop up our boxes enough to use more than 100 cores. And this meant that we needed new layers of parallelism. And this is where the kernel comes in, because on the kernel, we can just use one box and then harness all these extra layers of parallelism within the kernel to still speed up our code. And all of this, and that's the important point, like all of this without a major rewrite of the code. So we used essentially the old version of our code with a few tweaks, and that then just runs well on the kernel. This is our current status. So as you can see, we just performed a few tweaks. And then on the kernel, we got roughly a factor of 8 speed up. And in the final version of the code, the kernel is now 3.2 times as fast in a single socket Broadwell. And as I've told you, because of the way our parallelism works, this is the number that we're currently most interested in. But if you must have a comparison to a dual socket Broadwell, you can just divide this number by 2, and you're going to get a rough lower bound. Of course, there is still a lot to be done for the future, and in particular, at the moment, we have a lot of cache misses in our code, and the way we will try to solve this is by doing explicit prefetching, because in the derivatives, we actually already know a few hundred cycles in advance what data we're going to need, so it might be possible and beneficial to put some explicit prefetching into the derivative calculation. But yeah, all of this is work for the future, so for now, let me just thank you very much.
Thank you very much, Marcus. So maybe we stay put, and yeah. So everyone else to come on stage that gave a talk during the last lightning session.
Can you start on the stage? Okay. For the speakers.
So this is an opportunity to ask questions to the speakers. So fire away with questions. So we have one over here.
So a question for James. So in classical molecular dynamics, you can use Newton's third law in order to save half of the computations. And from your weight function, it also looked like you only distance. So are you doing that in somehow, or what is the reason to not do that?
To just reverse the sign, and then it depends, because it depends whether the particle's active or inactive. So it's not symmetric all the time. Depends on the case. So if one particle has the same smooth length as the other particle, in SPH the smooth lengths vary depending on the density of the region, whereas in molecular dynamics that's fixed.
Ah, I see.
So one particle might interact with the other, but it's not vice versa, if you see what I mean.
Yeah, okay.
John has a question.
So a question for James. So you said you do a merge sort, and I'm just wondering how much of your runtime is that? How much of is the overhead of that sort?
So we don't do this every time step. We try and do it every couple of time steps so that if the particles move out over a given threshold, then we do it again. But yeah, I need to look into that. Because the particular test case I'm looking at, we do the sort once, and then we do all the 26 neighbours, and that's the speed at I've been quoting there.
Okay, well, thanks.
Yeah. The total time spent in store is about 5% of the total runtime.
Okay, so it is quite small then.
It's a quite small fraction, but it gains a lot because you go from n square interaction to an O of n interaction in the pairs. It's a massive gain there.
I see. So when you said that it was 3x out of, I guess is it 16? Because it's single precision, so it was.
Yeah. So this is the KNL results.
Right, for the KNL
last
results. Yeah, exactly.
Yeah.
So if it's not the sort, where is the overhead?
The overhead is populating the cache and actually finding the neighbours.
I see.
So
Okay.
the column on the left-hand side is an idealized case where you have all the neighbours in contiguously, and that's like the maximum speed you could get for the interaction itself. Whereas the one on the right was populating the cache and then finding the neighbours at the same time.
Okay, got it. Thanks. And I have a question for Marcus as well. So you said you had a scalar remainder loop, and I'm just wondering if you've considered using the masking available in AVX 512 to vectorize the remainders as well.
So yes, at the moment we have this scalar remainder loop for flexibility, but because we can set a blocking factor in a standard application, we would actually make sure that that our boxes are multiples of the vector width, so that we don't actually have to iterate through this. So yes, in theory, we can definitely optimize this, but I think it's just easier to make sure that the boxes are multiples of the vector width at the moment.
Okay, that makes sense.
Yeah.
Thanks.
A question here from Juha.
Yeah, it's funny to ask a question for your co-author, but I noticed that you don't mention what's a normal run length. You mentioned about that the benchmark is 1,000 time steps, but that doesn't tell anybody how long portion of a real runtime that is. So how many time steps does a normal simulation take?
A normal simulation, so let me do the calculation. So that it depends on which level you are. On the coarsest level, we'll be taking 100 to 200 steps, but then that means on the finest level we might be taking, so if you have 8 levels in your AMR, that means you take 2 to the 8 times 100 time steps. So yeah, I mean, depending on how many levels you use, you'll be doing a lot of time steps.
Okay, any other questions? Ravi has one.
Hi, question to the last speaker. So you mentioned that there was a problem with division when running on KNL. It had some overhead. So did you try converting into a multiplication operation?
So I mean, so obviously the first thing you could do is like inversion and then multiplication. What we did in the end actually is for all these divisions, we noticed that we could just get rid of them and move them out, do the division once and for all, and then just multiply by the inverse. So we didn't really have to do this in place. We could just actually do this division once and for all, because they were all things that we were dividing by several times in the code. But as I said, on the Broadwell, none of this mattered. So we physicists were just tempted to write the equations as we see them on paper and not worry about the divisions. And then on the KNL, we saw in VTune that actually it started to matter because VTune pointed directly at the VDIF instruction in the assembly. So yeah, that's when we then just said, okay, we can actually just calculate this once and for all and multiply. And this is how indeed we got this 20% speed up. Yeah.
So one more question. You spoke about putting boxes on KNL, right, and on Broadwell as well. So the way I see it is, on Broadwell, there's a QPI involved between 2 sockets. But when you're running it on KNL, there's an interconnect involved. Okay. Mm-hmm. So is that a fair comparison?
So I didn't fully understand the question.
So you were putting boxes on dual sockets of Xeon, right? Mm-hmm. So between 2 sockets, there's a QPI involved. Okay, and when you're running on KNL, multiple KNLs, there's an interconnect involved. So is that a fair comparison?
Well, I'm not entirely sure what you mean, but the point is that if we're interested in the maximum possible speed we can get, we can put one box on each KNL, and then obviously the communication between the dual socket or the two sockets on the Broadwell is going to be faster, but than the communication between two KNLs. But in the end, we still have to use two boxes. So yeah, it just depends on what your runtime is going to be when you actually scale up to the full problem size.
Okay, any other questions? We still have time. If not, then let's thank our speakers again. Yeah, so that's exactly what I was going to do. So there is a networking reception in half an hour, I think, officially at least.
I think we might be able to start at
So
6.
yeah, so UHAS says we can start at 6. I just want to point out again that that networking reception is sponsored by Dell. I don't know if Gilles is the only representative from Dell here today, so thank you again, Gilles. You're picking up the tab. It's upstairs, exactly, yeah. So that's the most important thing. It's just upstairs where we were having lunch earlier on, so do join us. Make sure to come. Yeah, and tomorrow registration for anyone, obviously not here, but anyone that's coming starts at 8:30, and the session starts at 9 tomorrow. So it starts with a vectorization session that John is chairing. And another thing to point out is that all of today's presentations are available on the event webpage as PDFs, so you can access them straight away as of now. Yeah, for today. And I'll start rolling for tomorrow, yeah. Exactly. Thank you, sir. Well done. Very welcome.